Have you ever wondered what's really happening when you, say, save a file, or even just type a letter? It feels instant, but behind every single click, there's this hidden world of rules and requests that's basically keeping your computer from falling into total chaos. We're going to pull back the curtain on that world today. This is all about system calls, and once you get them, you'll understand how your computer actually works.
So it all boils down to this one question that we can all relate to. We've all been there, right? An app just freezes up or crashes. But why is it that that one program can completely fail while the rest of your computer, your music, your web browser, everything else just keeps on chugging along like nothing happened? The answer to that is pretty much the secret to all of modern computing.
To get it, you first have to understand that your computer is kind of living a double life. Seriously, it operates in two completely separate worlds, or modes, and it does this to protect itself, well, basically to protect itself from us and the programs we run.
Okay, so on one side, you've got user mode. Think of this as a safe little sandbox. It's where all your apps live, and they have very limited access to the computer's hardware. If an app crashes in here, no big deal. The mess is contained. But then there's kernel mode. This is the VIP lounge, the all-access command center where the core of the operating system runs. Anything in kernel mode has ultimate power, but if it crashes, it takes the entire system down with it. Blue screen of death, the whole shebang.
So you've got these two totally separate worlds, right? The safe little user sandbox and the super powerful but also super dangerous kernel space. So how does a normal app, like a game or a word processor, do something important, like save your file to the hard drive, without risking a total system meltdown? It needs a safe way to cross that bridge.
And that bridge, it has a name: the system call. A system call is the official, managed, programmatic way for an app in user mode to ask for a favor from the all-powerful kernel. It's like the bouncer at the door of that VIP club.
And this, right here, is the most important part. The app isn't just kicking down the door and taking control of the hardware. No way. It's politely knocking and asking the kernel to do the work for it. And that simple act, asking for permission instead of demanding access, is what keeps our computers stable.
Okay, so what does one of these polite requests actually look like in practice? Let's follow the journey of a single command, all the way from a line of code, down to the kernel, and then all the way back.
What's really interesting is that programmers almost never make these system calls themselves. Instead, it usually starts with a really simple command in a programming library, something like printf in the C language, which just means, hey, print this text on the screen. The programmer only needs to know that one simple command, not the super complex process that's about to kick off. This whole request follows this really precise 5-step dance. First, the application makes that simple request, the API call. Second, a software library acts like a translator, turning that simple command into the specific system call the kernel can understand. 3, and this is where the magic happens, the computer does something called a context switch. It literally flips a switch and goes from user mode into the protected kernel mode. 4, now that it's in its safe space, the kernel does the actual work. And finally, step 5, the computer switches right back to user mode, handing the result back to the app.
You can see that whole round trip visualized here. It's a very carefully controlled process. The app's request crosses this hard boundary into kernel mode. The system call interface makes sure it goes to the right place, the kernel does the job, and then the result gets passed safely back across. It's this beautiful, clean, secure journey every single time.
Okay, but hold on a second. That raises a pretty obvious question. The OS knows the app wants to, say, write something. But write what? To where? Just knowing the command isn't enough information, is it?
Right? So this is handled by passing along extra info called parameters. And one of the most common ways to do this is for the program to just pack all the details it needs, the text it wants to write, the file name, all of it, into a little block in its own memory. Then it just passes the address of that block to the kernel. So it's basically saying, hey, everything you need to know is over there. The kernel can then just go to that address and get its complete to-do list. Pretty efficient.
So we know how a program asks for things, but what exactly can it ask for? What's on the operating system's menu of services?
Well, they're usually grouped into 6 big categories. You've got process control, which is all about starting and stopping programs. File manipulation, that's for reading and writing files. Device management, for using things like your screen or a printer. Information maintenance, for, getting the time or system data. Communications, for letting programs talk to each other. And finally, protection, which is all about managing permissions.
And these aren't just abstract ideas. These are real tools that operating systems you use every single day are built on. So to create a file in Windows, an app uses a system call called create file function. On a Unix-based system like macOS or Linux, it uses one called Open. They have different names, but they accomplish the exact same thing using this same secure process.
What's absolutely fascinating is how these little building blocks get chained together. A task that seems super simple to us, like copying a file, is actually a whole long sequence of these system calls. The program has to ask the OS to find the original file, then ask it to open it, then ask to create a new file, then loop through reading from the source and writing to the destination. And then finally, it has to ask the OS to close both files. Every single one of those steps is a separate, secure request to the kernel.
Okay, we've gone pretty deep into the mechanics. Let's zoom out a little and talk about the big picture. Why is this whole hidden architecture so critical to the way our computers work?
This quote really just nails it. This entire complicated dance of different modes and context switches and system calls, it's all deliberately hidden from the person writing the code. This idea is called abstraction, and it's what makes it possible for developers to create amazing software without needing to know the nitty-gritty details of every single piece of hardware in your machine.
So here's the key takeaway. This entire hidden system, this is the invisible foundation of modern computing. System calls are the gatekeepers that allow powerful multitasking computers to even exist without constantly crashing. They provide the stability and the security that we now completely, 100%, take for granted.
So I'll just leave you with this final thought. This system call mechanism, it's basically a protective wall between every app you run and the very core of your computer's hardware. So just imagine for a second, what would our digital world look like without that wall? A world where any single buggy program could cause a total system meltdown. It really makes you appreciate the silent, invisible work that system calls are doing every single millisecond of every day, just to make our digital world possible.